Dear students, today we are going to see another important concept called Cauchy's integral formula. Before we are going to find the Cauchy's integral formula, we'll first find out the basic things about the Cauchy's integral formula. We'll prove the theorem. The theorem is nothing but the point is the concept, the index of a point with respect to a closed curve. Now, if you take a point in a closed curve, what is the index of that one? How you are going to represent that point? Whether the point is inside the closed region or it is in the outside the closed region. So, for that sake, now we are going to find out a theorem which says that suppose gamma is a piecewise differentiable closed curve. Let A be a point on gamma. A be a point on gamma, not on gamma, sir. It is not on gamma. A be a point not on gamma. Suppose, for example, this is a closed curve. Okay, gamma. A B is not on the point, not on the gamma. It may be inside the gamma, like this A. Okay, so like that. So then integral gamma dz by z minus a is multiple of 2 pi i. Now it is nothing but multiple of 2 pi i that we are going to find according to the. It is nothing but we can do it in a problematic manner. We will get 2 pi i. But in a theorem wise, how to prove that? That we are seeing. So what is that now? We shall prove the theorem by computing the integral given in the theorem. Now we'll try to prove. This is already we have proved by taking that mod z is equal to 1. We have got that 2 pi i. But in a theoretical way, how to find out that? Suppose gamma is nothing but z is equal to z of t, where t is nothing but in between alpha and beta, and we have to consider a function that is h of t is nothing but equal to alpha to t z dash of t by z of t minus a dt. And where h of t is nothing but it's a defined and continuous in the interval alpha comma beta. So therefore h dash of t is nothing but z dash of t by z of t minus a, where t belongs to alpha comma beta and z dash of t is nothing but continuous. Now we'll take this h dash of t to this side, means we'll take this z of t minus a to this side. You will be getting as z dash of t value. Okay, and we'll consider another function g of t. Now how the g of t will be? We are going to take that function such that you'll be getting in the form of like this. So g of t we'll consider in the form of like this. So we'll write g of t is equal to e power minus h of t into z of t minus a, where t belongs to alpha comma beta. Okay, now this is what we have chosen. Now we'll try to find out g dash of t. Now g dash of t is equal to, I'll just differentiate with respect to this one in the uv form. So I may differentiate e power minus h of t into z dash of t. Just I have u v dash I have taken, and this is minus because e power minus h of t into z of t minus a into h dash of t, because e power minus h of t, if you differentiate you will get e power minus h of t, and the differentiation of h of t is nothing but h dash of t. So in this e power minus h of t is common, and you may get it in the form of like you will be getting as z dash of t minus z of t minus a into h dash of t. Okay, now from here if you take this one to this side, you will get the value z dash of t. So you will be getting as e power minus h of t into z dash of t minus z dash of t. So that is nothing but 0 you will get, because this is 0, this will be 0. So z dash of t is nothing but 0 you got. Means you got z dash of t is nothing but vanishes at this point. Okay, so what is that now? Therefore what we can say, z dash of t is vanishes except perhaps except perhaps at a finite number of points, and since g of t is continuous, and it reduces to, and it must be reduces to a constant. So it may be reduces to a constant. It is continuous, so g dash of t you will be getting as some g of t is equal to some constant. You will get some constant. So what you got is g of t is nothing but you got as a some constants. So therefore what we can write here is, I may write that as, therefore I can write g of alpha may be equal to some g of beta. Okay, g of alpha is nothing but equal to g of beta. So I can write in the form of like this. What is g of alpha? G of alpha means I can make use of this. So e power minus h of alpha into z of alpha minus a is equal to e power minus h of beta into z of beta minus a. Okay, so z of alpha and z of beta will be equal because it's a closed curve. So I may write as e power minus h of alpha is equal to e power minus h of beta. Since z of alpha is nothing but equal to z of beta, because gamma is a closed curve. According to that, since gamma is a closed curve, these both are equal. Still I may write in the form of like this. Still I can use that one in the form of like this. What is that now? I may write as e power h of alpha is equal to e power h of beta. Okay, so e power h of alpha equal to e power h of beta. So therefore from first equation what we can write that, moreover, but what is that now? H of t is nothing but equal to integral alpha to t z dash of t by z of t minus a, where t belongs to alpha comma beta. This we have already chosen. You take it as this as some equation star. Okay, now I'll find out h of alpha. H of alpha is nothing but alpha to alpha z dash of t by z of t minus a, where t belongs to alpha comma beta. T belongs to alpha comma beta. So therefore what is that answer you got now? Z of alpha. So h of alpha is this. So therefore h of alpha is nothing but equal to 0. You got as h of alpha is equal to 0. So you may take h of alpha is equal to 0. So therefore e power 0 is 1. So e power h of beta, that implies e power h of beta equal to e power 0. Okay, because h of alpha is that. So I may write as e power h of beta is nothing but equal to 1. I may write as h of beta is equal to some 2 pi and n I am taking, where n belongs to some integers, because this is e power 0 is 1. So you may write this as some e power, I can say e power 2 pi I. E power 2 pi is nothing but cos 2 pi plus I sin 2 pi. So you will be getting as this cos 2 pi is nothing but cos n pi is 0. Cos 2 pi is nothing but it's a positive 1. Cos pi is minus 1, but cos 2 pi is 1. So you will be getting like this. N I have taken, I can choose any value of n. N may be 1, 2, 3. So what is h of beta is nothing but 2 pi n. So therefore what we can say that, so h of beta, what is h of beta? So therefore I can write that, therefore integral gamma dz by z minus a is nothing but equal to some 2 pi I n. That is nothing but it is a multiple of 2 pi n. So whatever it is, dz by z minus a is nothing but 2 pi n. Now this is the index of a point with respect to a closed curve. This is the way of doing this theorem, and also you can do this one in the form of, in another manner also you can do. So how you are going to find out that, we'll try to find out. Integral gamma dz by z minus a, where you can take t or theta may be taken as some 0 to 2 pi if you take like this, and gamma z is equal to some r if you take. Okay, so what is that now? Z is nothing but equal to r e power I theta. If you take it like this also, you can get it the same manner. That is nothing but dz is equal to what? Dz is equal to r I e power I theta. Now what we can write now? Integral gamma. Gamma is nothing but 0 to 2. Theta is 0 to 2 pi. So I will take 0 to 2 pi. Then dz is nothing but r I e power I theta. This is d theta. Okay. R e power I theta d theta by z minus a. So z minus z minus a means I may write as mod z minus is equal to r. This may be a plus r e power I theta. So what you will get now? Z is nothing but a plus r e power I theta. A plus r e power I theta minus this is a in the place of z. So this is nothing but a closed curve which we have chosen the point A. Okay, the radius is nothing but r. R is the radius. Now therefore what you are going to have here is you will get as 0 to 2 pi r I e power I theta by this a gets cancelled. You will be getting as r e power I theta d theta you will get. Okay, this is d theta. Okay, so r gets cancelled, e power I gets cancelled. You will be getting as integral 0 to 2 pi I into d theta. That is nothing but I into integral 0 to 2 pi. You will get theta and d theta. So you will be getting as I into 2 pi. Means you will be getting as 2 pi I. This is the problematic manner where you can do that. It is nothing but integral multiple, that is nothing but 2 pi I. So this is what we have done. This is nothing but called as the index of the point on a closed curve. The point which is nothing but with respect to a closed curve which you got. So this is how we got. So what the definition? Now we will have one more beautiful definition. If you understand this definition, the above theorem is nothing but is application of this definition. You can apply that theorem to the application. Suppose it's very important. Suppose gamma is a closed curve. Now we are taking as gamma is a closed curve, and let A be a point not on gamma. A be the point not on gamma. Then the index of the point A with respect to the curve gamma, which is denoted by n of or eta of or n of gamma comma a, and is defined by n of gamma comma a is equal to 1 by 2 pi I into gamma dz by z minus a. This is what we are going to find out. N of gamma comma is equal to 1 by 2 pi I and integral gamma dz by z minus a. Okay, this n of gamma comma a is called, is also called very important point, also called the winding number of winding number of gamma with respect to a. This is called winding number of gamma. N of gamma comma a is equal to 1 by 2 pi a dz by z minus a. This everything can be called as winding number of gamma comma a. So let us suppose this is the point A. If you take a circle, that is nothing but gamma. So how many times it is rotating? That depends upon the value of the the curve. It is winding. It is just winding number of n of gamma comma a. That is nothing but this is only one time repeated. That is nothing but 2 pi I. Now what we have done in the previous, the 2 pi I n. N is nothing but the value which is there. So here it is nothing but 2 pi I. So this is how we call as winding number of gamma comma a. This is very important point, that n of gamma comma is nothing but equal to this one. So therefore we have some properties regarding this winding number. This is very important to solve the problems. So this is a basic thing that you have to understand. Therefore you will be getting as you can easily solve the problems. Now what are the properties of n of gamma comma a? there are two properties. The first property is n of gamma comma a, n of gamma comma a means n of minus gamma comma a is equal to minus n of gamma comma a. This also we can write minus of n of gamma comma a. The second one, n of gamma plus gamma 1 plus gamma 2 comma a equal to n of gamma 1 comma a plus n of gamma 2 comma a. This is another important. These are two properties. Now how to do the first property, the proof of the first property. N of minus gamma comma is equal to minus of n of gamma comma a. Now we'll write this one. First we'll take LHS. LHS is what? LHS is nothing but n of minus gamma comma a is equal to. Now according to the formula, what is n of gamma comma a? N of gamma comma is equal to 2 pi I integral gamma dz by z minus a. This is the winding number of n of gamma comma a with respect to the a. So the same thing we'll write here. This is 1 by 2 pi I integral over minus gamma dz by z minus a. Okay, this is what we have according to that form. So therefore I may write this as minus 1 by 2 pi I integral gamma dz by z minus a, according to the theorem that minus gamma can be written as minus of this integral and everything. So what is this minus of? This everything is again n of gamma comma a. So like this we can do the property of this one. In a similar fashion, the second one also we can easily solve. See why I am doing this all, because to get the to solve the problems easily, we are going to solve the problems with the help of this. Now next second one, n of gamma 1 plus gamma 2 comma a. I am taking LHS, directly this proof. LHS I am taking. So this one I may write 1 by 2 pi I into gamma 1 plus gamma 2 dz by, I am writing as dz by z minus a, like this. So if I write like this, I can write that 2 pi I into gamma 1 dz by z minus a plus integral gamma 2 dz by z minus a. Just I have divided, I have made into two parts, gamma 1 plus gamma 2 according to the theorem, that is also. So I may write as 1 by 2 pi I integral gamma 1 dz by z minus a plus 1 by 2 pi I integral gamma 2 dz by z minus a. This is what? Now this is what? This is n of gamma 1 comma a plus n of gamma 2 comma a. This is another way of finding this one. So these are the two properties that we are going to use in the theorems. Okay, in the problems, to solve the problems we are going to do. These are the properties of index of the point with respect to the closed curve. So there is another important concept is there. Now let us suppose this is nothing but a circle. Okay, this is one more circle and this is another circle which I am taking over here. This is another curve. This is a closed curve. This is also a closed curve. Now the point is, this is the gamma. The point I am taking as a. The point A is outside. Now I want to find out the index of the point of gamma with respect to this A. Now what about the n of gamma comma A to work to this point? What is the value of n of gamma comma A? This one. Whenever n of gamma comma A is there inside, that also we should find out. Whenever gamma comma A means the point which is there inside, the value we should find out. The point which is there outside also we should find out. Now according to this one, we'll try to find out what is that now. What we have is, I'm just taking like this, n of gamma comma a is equal to, I'm just taking as 1 integral gamma dz by z minus a. I'm taking, this is what I'm taking, where f of z is equal to some 1 by z minus a. I'm taking, this is f of z is equal to 1 by z minus a. I am taking. N of gamma comma is equal to dz by z minus a, which I am taking. So what I will get now here is n of gamma comma a is equal to integral gamma, this everything, this is nothing but f of z dz. Now according to Cauchy's integral, Cauchy's Gauss-Seidel theorem, this f of z is nothing but analytic. F of z is nothing but analytic. Whenever f of z is analytic inside the region, then I can say that this is nothing but 0. So n of gamma comma a is nothing but 0. So what the A is there? Where the A is nothing but in the outside. So winding number of n of gamma comma A is nothing but which is outside is 0. There is there is no curve which is nothing but covered with the help of A. There is no cover. We cannot see that there is a closed curve here. So winding number of n of gamma comma A with the point, which of the point is outside, that is nothing but 0. So n of gamma comma A is nothing but 0. This is with respect to the Cauchy's theorem, Cauchy's Gauss-Seidel theorem. According to Cauchy-Gauss theorem, this is nothing but 0. So n of gamma comma is equal to 0. So this is how we can find out that the point which is not in the closed region, for that the n of gamma comma is nothing but equal to 0. This is how we can have. So now we'll solve the Cauchy's integral formula.